Hello, welcome to GT SciOly's Reach for the Stars and Astronomy workshop. My name is Sophia Wong. I'm a first year student here at Georgia Tech, and I'm part of GT SciOly, and I'll be leading this workshop for you guys today. So let's go ahead and get started. So this is kind of an overview of what we're going to be talking about today. First, we're going to briefly go over the rule sheet. Hopefully you guys have read it at least, but if not, we'll just touch on the most important things to note. Second is the difficult topics across both Division B and C. And then third, we'll go into some practice questions. Fourth is tips from me. And then five is some other free resources that you can use. So first, the rules sheet. So I want to emphasize that every single word mentioned, even briefly, should be somewhere in your notes, and even some topics that aren't mentioned. So, for example, you look at this and there's a lot of words here. Red giant branch, asymptotic giant branch, planetary nebulae, all of those need to be defined in your notes. Because I know this seems sort of obvious because if they're on the topic list, you need to take notes on them, right? But the you need to go a lot more in depth than many people think. Like it's not as simple as just defining the terms that you see and then moving on to the next topic. Like, oh, I know what a neutron star is now. It's you need to know the things surrounding them, like how they were created, or what stage of stellar evolution they're in, or their typical mass, some common examples, some standout facts, anything. So that's one thing I want to mention, even if it seems obvious. And another thing is that you should also keep a list of topics that aren't mentioned in the notes, but that you run across. Maybe like if you're on the Wikipedia page and you're looking at black holes and they mention some word that you don't recognize, then you should also add that to your list. It's not a priority, of course, but it won't be great if you're on the test and you see it in your notes and you don't understand what it means. So that's why it's good to keep a list of unofficial list of things that are good to know and that you probably should know, even if they're not on the rule sheet. So next is only for my Division C participants. This is about JS9, which is like the software to image stellar objects that it is in the rule sheet and it says you need to know it, but I will just say it here. It usually doesn't come up until higher level tournaments. For me, it didn't come up until Nats. But if you have the time, just learning the basics is all you really need to score a whole bunch of points. Not that many. It's not a huge part of the exam, but unrelated. So next is to pay attention when it says not limited to. They will and can test you on objects that aren't listed. So like here in the Division C rules, they say including but not limited to, and then they list a whole bunch of things that can be found in compact binary systems. But it should also be part of your job to search up what could possibly appear in a compact binary system. And if it's not on this list, even if it's not on this list, you should still put it in your notes. Okay, next tip is to spam specific object images. ID is absolutely 3 points and the most important step because if you can't identify it, you can't answer any of the questions about it. So you just need to have every single image of that object in existence in your notes. That's really important and not even that hard to do. You just Google it and put every related image on. So, in general, tests will be broken up into these sections. Specific objects first, and then general astronomy, and then math and physics. And then sometimes JS9, but like I said, it doesn't really show up. I wouldn't worry about it until much later. And that's only for Division C. So if you're in Division B, don't worry about that at all. Okay, moving on to difficult topics. You might have anticipated this, but it's physics. Yay. So physics is a really tough topic, in my opinion, every year, and it's always going to be there, so get used to it. My recommendation for my Div B students is to get the formulas with units because units are important. find out what all the variables stand for and understand the relationship it is establishing. Because almost every formula is going to have one relationship that's the one that's actually important, and everything else is just supposed to be plugged in or like constants that you don't really need to worry about. For example, Kepler's third law is t squared equals 4 pi squared over gm times a to the third, which looks absolutely incomprehensible, and if you just have this and you're on a test and you're expected to answer questions about Kepler's third law, you're going to be really lost. So I, for this one specifically, the main relationship it's establishing here is that t squared, where t is period, and a cubed are related, like directly related. And that's important because this means that for any planets that are orbiting the same object, their, how do I say this? Their period is proportionate to their major axis, which is their distance from the object that we're orbiting, basically. You can see kind of in this top right corner, that's the third law in simpler terms. Like this relationship, t squared, or it's p here, over m cubed, which is a cubed here, is the same for all planets in a solar system. And you'll notice this if you take the time to go through the formula because it's 4 pi squared over gm. Those are all going to be constant if the object that they're orbiting is constant because that's what the big M is, the mass of the center object. And g is gravitational constant. Pi and 4 are obviously constants. So yeah, like here the next point is that part of recognizing where to plug in numbers on a test is recognizing what a measure of period is or gravitational constant. That one's, the units can get messy. Clearly, this is Newton's 10 meters squared over kilogram squared. That's not pretty, but recognizing units is really important because you know if the units don't work out, then you've done something wrong. And that's a really good sign that something's not working out right. And remember that any physics is useful physics, even if it doesn't seem like physics. Like something as simple as the area of a circle can help you find things like orbital velocity, or it's really how you apply things that makes the difference. So don't discount any of your knowledge, and if you want to, you can even put in basic geometry formulas into your notes, and it might be helpful. It very well could be. I've used trig and random geometry formulas like area of a circle or circumference on astronomy tests. Okay, so continuation of this kind of Division C physics. A lot of the same stuff that I mentioned for Division B still applies. Make sure you know how and when to use the formulas. Don't just dump them into your notes and include units. Cannot emphasize that enough. But you guys get a little harder physics. Yay. I would recommend taking a physics class. It's really helpful for specifically all the like gravity stuff, since that is a unit in most physics, like AP Physics 1 or AP Physics C are gonna have a gravity unit, but um if you can't yet, don't worry about it. It's just really helpful to have that base knowledge, but you don't need it to succeed. Next is note that you can find the answer to physics problems using simple geometry at times. Like, and I mentioned this on the previous slide, but like if you're trying to find the period of a planet, it's just the time for a full orbit. So if you have radius of an orbit and orbital velocity, then you have speed and circumference. And from there, it's pretty easy to get to the time for a full orbit because you know how fast it's going and you know how far it has to travel. And same with distances. Parallax is just trigonometry, and we're gonna do an example later. And this is just a small note, but when they mention radiation laws in the rules, that's like Wien's law, Stefan Boltzmann law, luminosity and magnitude. Those are the main keywords that you should be going for. They don't really expand a lot upon it, so just wanted to mention that when they say use the radiation laws to answer questions relating to planetary surface temperatures and habitability. That part. Okay, third topic. This is Div C. Sorry, Div B again, but this is for JS9. And one thing to note is that you should not be scared of JS9. A little preparation goes a long way. It looks overwhelming at first, but once you figure out how to do like really just the basics, then you're pretty much set for the rest of it. So this is the main resource that I recommend. I will work through the guide for using JS9, and don't just copy paste this into your notes and try and figure it out on the day of. That will not go great for you. So actually try and do the activities. Um, yeah, that's just a small note about the interface. And yeah, it's well, you shouldn't copy paste the guide itself. You can like give yourself annotated notes. Like just so on the day of the test you can jog your memory, be like, "Oh yeah, that's where that button was." Like take screenshots, write down like what the steps are and paraphrase them in your own words, stuff like that. There's a small side note here that my partner added. She did much of the JS9 for us. She said that trying to pan around the image will mess up the colors, and that's how you fix it, because that's something she struggled with. It's a small thing, but. And yeah, this other tip here, if you need to look at image metadata, that'll give you a bunch of information about that image. And sometimes that's all you need. Like if you just have that, then maybe they were just asking about the telescope and then boom, you have it. So that's probably what you're gonna use most in JS9. All right, let's move on to some practice questions. I'll be giving you guys a little bit of time to try these for yourselves, and then I'll go over the answers. So up first, question 1, provide a 2 to 3 step explanation of how you can derive the distance modulus from the formulas for flux. So this is the distance modulus here, and these are the equations for flux that you're given. And I've labeled everything that you need. Some of them are missing units, but you shouldn't need the units unless they're listed. So I'll give you guys, 5 minutes? Is 5 minutes enough? I'm gonna say 5 minutes to do this problem. Wow, that's crazy. 5 minutes is up. Okay. So let's go over how to do this really quickly. I'm gonna pull out Sketchpad. It'll load. Okay, great. Now, so I apologize in advance for my awful handwriting because I cannot write with a mouse. But let's see. So we're starting here with the first flux equation, which is F1 over F2 equals 10 to the m 2, yeah, m2. Uh, m2 minus m1 all over 2.5. Yeah, really sorry about the handwriting. Okay, and then from here, the first immediate step I would notice is that you have another equation for flux, which is F equals L over 4 pi d squared, right? And more importantly, this formula has d, which is, if you'll notice, distance in parsecs, and r is distance in parsecs. And we really want to have r because that's part of our distance modulus equation. That's the whole point of it. And we do not have that in this first flux formula. So the question is here, what would be flux 1 and what would be flux 2 might be a question, because that might not be immediately obvious. And this is really just referring to flux for any two stars. But if we know about, and this was in one of my hints, absolute magnitude is the magnitude of a star from a distance of 10 parsecs away. And then apparent magnitude is its brightness from magnitude from Earth. So if we know that, then let's say F1 is the flux of the star from 10 parsecs away. PC, that's a C. Parsecs away. In other words, absolute magnitude. And F2 is the actual distance, which we're gonna just call R because they used R in the distance modulus formula, is from R parsecs away, which is the apparent magnitude. So I'm gonna change these units because M1, F2 corresponds with M2. This is going to just be the apparent magnitude. And m lowercase m is apparent magnitude, so I'm going to change this to m minus m. That's a capital M for absolute magnitude. And we can already see m minus m is part of our last formula, so that's a sign we're on the right track. And then this, we can just leave them as F1 and F2. So now we want to substitute in this formula for flux for both fluxes. So first one is going to be, oh no, let's just do the whole fraction. So this becomes L over 4 pi d squared, d1 squared. And let's do L1. L2 over 4 pi d2 squared. So you might not necessarily know this about a star, but the luminosity is always the same for a star. You could have gotten stuck here. That's my bad. I should have added a hint. But um it's not differing based on the distance like magnitude does. Luminosity is the same. And since we're talking about the same star, just observed at different distances away, we can actually cancel out the luminosities as we can with 4 pi because that's a constant, it's in both sides. So we just have 1 over d1 squared over 1 over d2 squared. So now, if you'll notice, d1 is corresponding to flux 1, which is at a distance of 10 parsecs away. So we actually know what d1 is. It's 10. So I'm just going to leave it squared for now. That's 1 over 10 squared. And then this is 1 over, and this distance, d2, is the apparent, which is the distance from Earth, which is the same as r. So this is 1 over r squared. And if you don't know how to simplify complex fractions, you basically flip it. So this becomes r squared over 10 squared. And now this is equal to 10 to the m minus m over 2.5. Because remember, this is the same as our flux fraction, which we transformed through the luminosity stuff into this. So I'm gonna really quickly uh delete. No, okay. Hold on. Okay. Start over with a clean background. So now we have r squared over 10 squared equals 10 to the m minus m divided by 2.5. And I made a note about this earlier, but in the hints, but taking the square root is the same as going to the 1/2 power. And that was supposed to be a hint at this point because, well, if you'll notice, these are both conveniently squared, and 10 is already to a power. So if we just take the square root of this, we'll get r over 10, right? And then on the right side, you can think of this exponent as the fraction n minus m over 2.5. It's the same, but now vertical. And now remember, taking the square root, and this wasn't the hint, is the same as going to the 1/2 power. If you don't know how exponent laws work, basically 2 squared, um, to the 1/2 power, you just multiply the inside power by the outside power, and it becomes 2 to the 1. And this also makes sense if you notice that 2 squared, the square root of that is going to just be 2. So we're just going to take the 1/2 power of this whole thing, and that's just multiplying these two exponents together. So you end up with 10 to the minus m over 5. Everyone see how I did that? Because 2.5 times 2 equals 5. Yep. Okay, so move this out the way. Now we have all over 10 is equal to, ignore all this, is equal to 10 to the m minus m over 5. And already it's looking a lot more familiar to this equation right here. And the last step just has to do with rules involving logarithms, which you all may not have learned yet, but it's just like, let me demonstrate really quick. So a to the b equals x is logically equivalent to log base a of x equals b. And how I got this was I did a little circle. So you can think in your head, first log base a of x equals b. Finally, just go in a little circle. And it's the same if you want to go back. A to the b power equals x. And you'll notice that's what it is here, a to the b power equals x. So that's how logarithms work, and we're just going to take log base 10, just like they did here, of both sides of the equation, because we still want it to be equal. I'm gonna get rid of some of this. It's a little much. So I'm gonna rewrite this, so give me a second. Gotta have a cleaner picture for you all to work with. Okay. Now we take the log of both sides. So we start at the 10, and we go log base 10 of all over 10 equals all this. And you can write that all out as log base 10 of all over 10 equals m minus m over 5. Wow, and this looks a lot like our equation right here. The last step is just to multiply both sides by 5, of course, and then this drops out. And that's our equation. We solved it. We have the distance modulus. You guys just derived the distance modulus yourselves. Wow, incredible. So yeah, this is a pretty hard question. I found it on a practice test for Division B Reach for the Stars for this year. I think that's pretty cool to give Division B, but just know that this can be the kind of thing that you might see, and just be prepared for things like this to come up. There's a surprising amount of algebra of like substituting in equations or numbers in and then solving for something else. That's a theme that shows up a lot in physics. So now we're going to go on to our next problem. Question 2. Parallax is usually measured in arcseconds. If a star has a parallax of 0.2 arcseconds, how far is this star from the sun in parsecs? And I've given you guys some conversions and some hints and some diagrams, very helpful diagrams. You should read the diagrams. But I'll give you guys another 5 minutes to try this one, and then I'll show you how it's done myself. Sound good? Okay, go. And then we pretend that 5 minutes happened because I'm not gonna sit here for 5 minutes. But I am gonna erase this really quick. Okay, wow, you guys did so great. Okay, time to go over this. So, let's start this problem with what they've given us. A star has a parallax of 0.2 arcseconds. How far is this star from the sun in parsecs? So, if you'll see in this diagram, this is the parallax that they're talking about, this angle P degrees. Oh, don't know what that symbol is actually, it's too blurry. But let's just recreate this right triangle in our notes. You can kind of see where I'm going with this maybe, but this is Earth. We're gonna call it E. This is the sun. Gonna call it S. This is the distance D to our star. And let's just call this star X. Beautiful. And then this is our angle P, of course. And we're given that P is 0.2 arcseconds. So now you may have noticed or you may not have, but this is actually going to be a right triangle. And the reason for this, that it's always a right triangle, is because we can just pick any arbitrary point in Earth's path to start calculating our parallax from, and we're always going to choose the one that's close to perpendicular so that it's gonna be a right triangle and we can do the easy math. But all right, let's start here. So I gave you some hints about the trig you're gonna need to use, but if you didn't pick up on that, the main one I want to focus on is that the tangent of this angle P is equal to the ratio of the opposite side over the adjacent side. And what does this mean? Well, the opposite side is right here, the distance between the Earth and the Sun, if you'll notice. And the adjacent side is our distance d. That's what we're trying to find, right? So this is our goal right here. And if you'll notice, we have P and we have our opposite side because the distance between the Sun and the Earth is always 1 astronomical unit. And this was kind of a hint here when I gave you this conversion, but yeah, so basically this is 1 AU, we have that, and this is 0.2 arcseconds. But we can't actually calculate the tangent of 0.2 arcseconds yet because no calculator that you probably own can do that. So we're gonna need to convert first. We're gonna convert units from arcseconds to degrees because most calculators do accept degrees. So let's just start here. This is how I convert units. You don't have to. Arcseconds and 3,600 arcseconds and 1 degree. Degree. That's really ugly. And you just divide by 3,600, which let me get my calculator really quickly. Okay. Is about 5.5 repeating times 10 to the negative fifth. Yay. And that's in degrees, and that's our angle P. So that goes in there. So we can actually go ahead and take the tangent of that. And the tangent is going to give us a very small number, 9.696 times 10 to the negative seventh. That's tangent of 0.2 arcseconds. And it doesn't have units because it's a tangent. And this is equivalent to 1 AU over adjacent distance D, which is our goal. So now let's solve for that. But we want our distance in parsecs. Note, how far is the star from the sun in parsecs? So we're gonna need to convert this AU in the top part to parsecs so that everything's in the same unit. I'm gonna get rid of this. And this. I'll keep the diagram for now. I think it's helpful. But now let's just convert really quickly. 1 AU, and I feel it's 206, 265. Nope, that's the wrong. How do I go back? AU is equal to 1 parsec. So now we just divide 1 by 206, 265, and you should get something like 4.85 times 10 to the negative 6 parsecs. And that's that distance here. So we're going to plug that in. If you multiply d to the other side and then divide by this, do you guys want me to write that? I'm going to write it out. So d equals 9.7 times 10 to the negative 7th. Oh no, that should actually be under 4.85 times 10 to the negative 6th. Yeah. So if we just do that calculation, in your calculator, you should get about 5.0. Boom! Done. Parsecs. Done. That's our final answer. 5.0 parsecs is the distance between this star X and the sun. And those of you who have done astronomy in the past or just know this formula may have picked up on something, but the formula for parallax is actually distance in parsecs equals 1 over angle in arcseconds. In other words, distance equals 1 over 0.2 equals 5. That was it. That was all you needed to do for this problem if you had the formula. But before you get mad at me, what I wanted to show here is that even if you don't have the formulas, that doesn't mean you need to give up on the problem. Sometimes you can find it from other ways. Like, we just solved this parallax problem purely with trigonometry and without the parallax formula at all, even though it would have been simpler. But that's, in my opinion, more important than having every single formula in your note sheet. Being able to work on the spot, find a solution, algebra it out somehow is way more important to me, especially in the physics section of astronomy. But yeah, I'm sure the trauma will make sure you never forget that distance in parsecs is 1 over p. All right, moving on to our last slide. So those were about physics, since those were the difficult topics that we were talking about. But the rest should be easier. These are sort of like general astronomy and one specific object question. I don't expect you all to get that one necessarily unless you've done astronomy before, but just kind of give you a brief glimpse of things that show up a lot, the kind of questions you're likely to get. So, and this goes for both Division B and C. These are a little easy for C, but they probably still will show up in the multiple choice. So, um, first one, what stage of stellar evolution is the sun in right now? Anyone want to put the answer in chat? Correct! It's in the main sequence. The main sequence star. Good job. Okay, next is specific object identification, which I don't expect you all to know for this one, but in case anyone does, please identify the stellar object in the top right, this picture right here, and what nebula is it in? Wow, I can't believe you knew that! This is the Mystic Mountain in the Carina Nebula. The Mystic Mountain probably wouldn't actually be a tested stellar object, but the Carina Nebula was. And this is just one specific structure within it. So, next, which of these phases is most likely to immediately follow a small red giant? A, B, C, D. Put some answers in chat. Blah, 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 blah. Wow, correct. It's a planetary nebula. There is also a series of events where it could explode in a giant supernova and become a neutron star or black hole, if any of you guys put that. But that is for a large red giant, and I did specify that it was small. So you need to know the multiple tracks. Next is what stellar object can produce a type 1a supernova and when does it occur? What causes it to occur would be a better question, I think. Answers in chat, blah 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 blah. Boom, it's a white dwarf, and when it exceeds its Chandrasekhar mass limit, 1.4 solar masses. So next, what is the heaviest element produced by nuclear fusion? Iron! Wow! Great, okay. Now moving on to tips from a veteran, me. So first off is about note-taking for specific objects. And this is about like everything you need to know for them. I've already said you need as many pictures as humanly possible, but you also need to know in general statistics, what makes them special, fun facts, what kind of object they are. Because usually if they're in your specific objects list, it's because they're special. Like they put them there for a reason. Something about them is unique or extraordinary or worth looking at, or they're just like very new. That's also possible. And also, yes, a billion images of everything possible in that object, around that object, anything to do with it. So next is I would highly recommend a formula constants and conversion sheet for math, especially division C. You'll run into it a lot. It's just so much faster to have it all in one place, be able to glance, see, oh, that's the formula I need, that's the conversion I need, those are the units I need, and that's how I get them. Next is astronomy tests usually will run long and difficult. Lots of questions, not a lot of time to answer them, and they're gonna be really hard. So my recommendation is that you and your partner split up the work. Just tear it in half if you're allowed to. Check that you're allowed to. Make sure you answer every single multiple choice, just guess, and then spend the remaining time on the long math problems because they're usually not worth as much points as they take up time. So that's kind of like treat them like a tiebreaker, kind of. And check the worth if it's taking you a while, like the amount of points that question is worth, because sometimes you can spend like 10 minutes on one problem and then look down and it's 2 points and it's not worth it. Absolutely not worth your time. Don't get hung up on questions, but especially not if they're not worth the points. So for personal process, I handled on tests, the multiple choice, specific object questions, and general astronomy topics, and my partner was really good at physics, so she did the physics and the JS9 if they had it. And small side note, this is not how you should split your note taking because note taking is much heavier reliant on the specific object and general astronomy topics. That's what most of your notes should and will be about. So you don't have to split the test the same way you split notes. Practice tests. You need to take as many practice tests as you can, and but don't just like blindly take them and be like, "Oh, I got a 37. Yippee." Don't just move on, okay? Just take the time, take note of the questions that you got wrong, take note of why. If it's a simple matter of you didn't have it in your notes, put it in your notes right then and there, or you're gonna forget and you're never gonna go back for it. If it's a matter of, oh, I misunderstood from my notes, clarify it in your notes. If it's a matter of, oh, I just had everything I needed and I just didn't come to the right conclusion or wasn't able to solve it, then that's fine. And then you don't have to actually do anything except maybe look over it and see the solution. So, and also you don't have to take practice tests until you're like pretty well through the notes, but they're a good way to check what you're missing. So, and this is for Division C because you're allowed to have either two binders or one binder, one computer, or two computers. I recommend two computers. Save the trees, guys, okay? Also, hyperlinking things like a table of contents and Control F will save you life on tests. That your notes should be too long for you to just easily flip through it. Control F can save your life and you're saving trees. Think about it. But if you prefer binder, of course, go with what works best for you. However you want to do it is what's probably gonna work for you. Next is that tests may care about information concerning specific photos as well. This is kind of a picky thing, but like on specific identification for specific objects, they can ask you, identify the nebula in this image. What light wave was the image taken in? What telescope was it? What star observation study was it from? Things like that. Like the pickiest things can show up. So even when you're spamming a billion images, take just a couple seconds to find out a little bit about where the image is from. It'll also make it easier for you to check that it's actually an image of the star that you're looking for and not just some random one Google threw at you because it's similar. And this isn't necessarily knowledge, but it's something I've noticed and kind of helps me on tests. If you don't know what wavelength it's in, you can kind of guess from the color. Like X-ray images tend to have bright purples and bright greens. Visible, like Hubble has a very distinct style of photos. They've got like dusty yellows and blues, and it's very vibrant and beautiful and in your face. And then infrared through radio is all like blurry, dull reds. So just small side note, you don't have to memorize that or anything. It's just something you get into recognizing when you've seen enough of the photos. So next point is to make sure to also research if your specific object has different names or smaller parts within them. Like maybe a lot of these are gonna be listed like in your topics list as like HGC 1337. And that's not, and maybe it's also called something like, I don't know, the blue planet. That's a really dumb name, I'm sorry. But um you can find way more pictures if you know all the names it's under. And if you know things that are in it, those can also help you like find better pictures or more specific pictures or even more facts about it, like more fun facts. Like the Carina Nebula, I've brought it up a lot, but it's huge, okay? It has a keyhole nebula within it, cosmic cliffs, Mystic Mountain, so many parts to it. And a lot of the photos that are of the Carina Nebula aren't are really far from the full thing. They're just like one tiny corner of it, and you need to recognize, okay, that's not the full Carina Nebula. That's one part of it. Because it's going to be confusing if you have like 50 different photos of the Carina Nebula and none of them look similar. So next is to make sure you have thorough notes on very important stellar objects. And these are things like the sun, the earth, the solar system. Those are the ones we're on, so they're very important and they will be tested on. Like you would not believe how many questions they ask about these things because they're like the baseline for all astronomy. Everything's like based around the sun, the earth, the solar system, where we are, all that. So you need to have, at the very least, facts like the mass, radius, magnitude, classification, orbital radius, period, etc. All those things. Like an actual question you can get on a test is just absolute magnitude of the sun. That's 3 points. It's easy. That's you should be able to like know that instantly, if not from your notes, then off the top of your head. Like that's 4.83. I just know that from having answered it too many times. So these are like really important things. And next is that stellar evolution is a really big topic that you're gonna see come up a lot. Uh, I would say it's even more important than physics. It's just physics is harder, a lot harder to do, which is why I put it in this presentation today. And make sure to check that your information that you're like putting in your notes is actually updated and credible and has not been disproven yet, because astronomy is a constantly growing field, kind of understaffed, honestly, with how big it is. Like, there's so much going on in the universe on every second, and they're learning so much more every day. So make sure that your information is updated and correct because, and this is kind of an embarrassing story, but uh, one photo, I was trying really hard to find an annotated map of one of my specific objects. And when I finally found one off of Google and tried to put it in my notes, I found out that it was actually sourced from fandom.wiki and was some fan created map of a fictional star nebula. So, yeah, make check your sources, guys. Check your sources. Okay. And here's my disclaimer. I may be mildly overstating the importance of physics to astronomy, and this will probably be a relief to most of you. I'd say is a good 1/4 to 1/2 of your points, easily. Sometimes even more. General astronomy is going to be another third to half of your points, and physics is usually 1/3 or less. It's the reason I'm emphasizing it is because it's harder, because everything else you can kind of just take notes for. You just learn about it, put it in. Simple, easy, clean. But physics is a little messier and a little less intuitive and not something you can prepare for as easily. But it's usually a third or less of your points, and it's like you can consider it a tiebreaker. Because if it's too hard for you, it's probably too hard for everyone else as well. Also, depending on the competition you go for, I mentioned this before, but JS9 often doesn't show up at all. For me, it wasn't at invitationals, regionals, or state. It was only at nationals, and it wasn't even that big of a part of the test as a whole, so just keep that in mind. Like, it can be low on your priority list. Next is that hopefully you will have all the notes and photos and knowledge to answer everything else on the test already. Physics is just a little more involved than Control F, which is why I went over it so much, but you shouldn't base your opinions of how important everything is based off of like how much I covered it because it's not accurate at all. I'm just Physics is kind of like a next level boss to reach after you have all the solid notes for everything else. Worry about the topics list first, and then worry about physics. And I mentioned this here, it's so much more important that you get solid notes. And yeah, my teammate really did download Wikipedia pages complete off the internet, and it did not work, so do not do that. He said he did horrible on that test and way better when he took actual notes. Keep that in mind, okay? And that goes for ChatGPT as well. If you just ChatGPT notes, then you're spending the entirety of your test trying to mangle through flowery sentences of words you can't understand and a bunch of vocab and things like, certainly I can give you a definition of this, blah, blah, blah. Don't do that. Just paraphrase it in your own words. And the point of notes isn't so that you can learn it on the day of the test. The point of notes is that you've already learned it when you're studying the material, and then you can jog your memory when you look at your notes. So, good notes should not need to be long at all. Okay, but hopefully I haven't scared you off of astronomy yet. Promise it's cool. You learn so many cool things, and it's just this cool topic in general. But that's it from me. Here are just some additional resources. Practice tests, yeah, specific object images, picture of the day, and Chandra website. A lot of the official telescope websites are really helpful. And yeah, that's all I have for you guys. Thank you for your time. Do you guys have any questions? Boom. Yay.